Good afternoon and welcome to Troubleshooting Query Plans Part 2. This is where we will continue looking at various query problems that we've resolved to not be caching problems, and instead we know that there's some kind of statistics problem going on, or just some kind of query problem that we can't quite get to, and we know that we're not using a cached plan. So what we're going to do is dive in and figure out kind of what we can do with statistics, or where we can go, what we can look at, and where in fact the problem might be. So quick introduction to the session and to the slides and me. I've been working with SQL Server, like I said, for like 30 years, and SQL skills for 25. You can read all of this great information on here, and I just want to get into the technical stuff. That's my favorite anyway. So as far as this session, and if you didn't see the session yesterday, you'll want to go back and look at some of that content, because you really need to figure out first if it's a caching problem, or if you're positive that it's not a caching problem, that, okay, where can we look if we think it's statistics, or we're not sure what's going on with that query. So we are sure that it's not a caching problem. So at this point we see and are going to look at things like the selectivity, the estimates. We're going to get some ideas behind compatibility and cardinality estimation models. And then we're going to look at some specific limitations of statistics themselves. And I'll give you some insight into things you could do to update stats with full scan, filtered stats, or even some cases where SQL Server just can't come up with the right estimates. So what do we do? So, all right. Everything about your query in terms of how SQL Server optimizes it starts with how many rows that SQL Server thinks it's going to process. And if somebody tells me, oh, my query returns 1,000 rows, is that selective? I don't know, because if there's only 1,000 rows to be processed, then obviously 1,000 out of 1,000 is not very selective. So really, selectivity is always relative to the amount of data that's possible. Now, that is even a loaded question in and of itself. What percentage out of the rows possible would make something selective? And if any of you have been through any lectures of mine on indexes and this thing called the tipping point, and kind of how SQL Server determines what indexes to use and how to process your query, you can even find that selectivity is kind of a loaded question in and of itself. So when is a query selective enough to warrant using the index is a big it depends. And it depends on the query, the predicate, it depends on joins. There's actually a ton of factors that go into whether or not SQL Server should use an index. Now, if there's just one predicate, one where clause condition, then it's not so difficult for us to determine and to see. But as soon as you start adding multiple conditions, multiple joins, it starts to become more and more complicated as to how SQL Server calculates whether or not they should use an index and what plan they should use. I would even argue that it's not something that you would want to waste a lot of your time on trying to figure out all the individual calculations and how to make something work differently based on number of rows or any. I think it's interesting to know some of those things, and I think it's interesting to see some of those things, but I wouldn't get wrapped up in it. What I want to stress is that as you change cardinality estimation models, as you change queries and indexes, it can get complicated as to how SQL Server figures all this stuff out. So there's lots of things to consider, and I think probably the most important is this last bullet on this slide, is there's a lot of decisions for SQL Server to make, and not all of those decisions work all of the time. So we have to get a little bit of insight into what's going on so we can kind of make sense of things. I would argue, though, that the most important thing to do is to give SQL Server the best information it has about processing your data. Like if you think about it, if your query has to process one row, that's going to be a very different process to process that data than if your query has 1,000,000 rows. So everything in terms of how SQL Server optimizes and calculates is all tied to how good its estimates are. And so the better the numbers are that are feeding into this incredibly complicated process, the better those calculations are going to be. So that's probably what I would say is the most important thing you can do, is make sure that you have good statistics and make sure that the things that could potentially cause that selectivity and estimation to be bad are as optimal as they can be. So let's see and talk about what affects it. And I really like to talk about the complexities of cardinality estimation and compatibility mode. For a long time, compatibility mode or compatibility model, depending on who you talk to and what day of the week it is. But this thing called the compatibility mode originally was really meant for you as a developer to have time to fix your code as you're migrating up to a new version of SQL Server. So the idea was, let's make sure that the keywords and so forth don't throw errors if there's new keywords. So let's make the code run as if it's compatible with the older version. Now, this has gotten more complicated over time because they've added in things like optimizer fixes and so forth. So over time, they changed essentially a little bit about what compatibility mode did. And in 2014, they made the biggest change to it. And I'm actually not that big of a fan of this. I wish that cardinality estimation had not been thrown into compatibility mode. I love that in 2016, it's separated and is now better set through a scoped configuration option. But in 2014, if any of you are still running 2014, it's a little bit funky because if you change your compatibility mode to 2014, you get the new CE and you get the optimizer fixes and so forth. But you can't really get the optimizer fixes without using the new CE unless you change individual code or you change a server trace flag. And I think that's a little bit not what I want to do. And I did list it on here. You can get the optimizer fixes if you want just those with the trace flag 4199. In 2014 and higher, the compatibility mode includes all the optimizer hotfixes up to RTM. That's kind of interesting too, because if you're on 2019 SP2 or whatever, you do not have all the optimizer hotfixes up to SP2. You have all of the optimizer hotfixes up to RTM. And if you want all of the optimizer hotfixes up to SP2, then you can also use the query optimizer hotfixes scoped database compatibility model. So this is a little bit confusing. I would take a little bit of time to get comfortable with this, but my recommendation as of 2016 and higher, especially for a lot of you that are upgrading, I usually, and I have a summary slide that will bring this all together, but I usually recommend that if you have a database that's been around for a long time and it's been well tested and well tuned on earlier versions of SQL Server, let's say you're on 2014 or you're on 2016 and you want to go to 2019, what you might want to do is upgrade to 2019, change the compatibility mode to be 2019, but then set the cardinality estimation model to be the legacy CE if your database was more optimized for the legacy CE, the CE prior to 2014. So if that database has been around for a long time and you haven't done a lot of testing with the new CE yet, then at least you can set just the CE down to the older CE. And at least you can get the optimizer hotfixes up to RTM of the release that you're on, which is really cool. Okay, so I think my favorite thing, though, is that you have two CEs. I kind of hate the designation that legacy CE implies bad or old. So let's talk about what the CE affects, because I think this is important to understand. It's a way of calculating and estimating how much of your data matches some criteria. I like to imagine a products table. Imagine you sell products. Now, think about this for a second. Your products have a shape. I mean, this is generic, but I just want to throw some numbers out there for a second. Your products have a shape, and let's say, for this example, that 33% of your products are round. Okay, so this is pretty easy. A third of your products are round. Now, all of your products also have a color. And I'm going to say that 25% or a quarter of your products are red. Now, assuming that we don't have any indexes that bring shape and color together, and assuming that we run a query that says something like, I want to know, select star from products, where shape equals round and color equals red. So we're putting those predicates together. We have individual indexes on shape and color independently, but no indexes with them together. The question starts to ask, well, how many products are both round and red? Now, what the legacy CE did for its calculations is it basically assumed even distribution. So if 1/3 of our products are round and a quarter of our products are red, then you can basically say that a quarter of a third of our products, 1/12, would be red and round. Okay, so the legacy CE would basically say 1/12. The new CE essentially says, we don't think that everything is going to be perfectly evenly distributed. Let's back off a little bit on these calculations. And when it does its calculations, it takes the fractions after the lowest. So it takes first the lowest fraction of the ones we're calculating, which is a quarter. And then it starts to back off of the next fraction. So 1/3, it basically squares that third to a ninth, and it multiplies that out, and we get 1/36. Now, in a lot of environments, that might be better to not assume even distribution. In some environments, even distribution might be the more accurate estimation for you. So here's my problem with the different CEs is neither is always going to be right all of the time. Now, they did find in a wide variety of their tests that the new CE was more accurate across a wider sampling. And that may be very true. But depending on your environment, you might actually find that for certain data, for certain columns, for certain environments, that the legacy CE may provide better estimations for you. The coolest thing, this is my favorite, is that as of 2014, yes, you pick one that is essentially the default, but you can use and change the CE on a query by query basis if you need to. In fact, I would even throw this out there. What if all of your red products are round? Like, think about that. Okay. If a quarter of our products are red, right? That means that there are a quarter red, a third round. So there's fewer red than round. But imagine that red products are round. Well, that would be something that we would call minimum value estimation, which in the legacy CE you could implement through a trace flag, and in the new CE you could implement through a different trace flag. And part of why they did this is that if your queries have trace flags, they want to make sure that those trace flags make sense. So let's change the trace flags so that we have to verify and check all of that code. So this is minimum value estimation. My point that I love is that there's always a way to kind of get what it is that you want to be the estimation. And I wouldn't argue that everybody's going to know their data distribution this well all the time. I just like this example because it gives you insight into the fact that the legacy CE and the new CE are different. Okay, and even though the new CE might be better across a wider variety of the different sample databases, it may or may not be good for your data. And in fact, it might be that you need something like minimum value estimation for certain patterns. Now, you're always better off having indexes that can help correlate the columns with an index on multiple columns. So that brings a whole nother question into play, which is, could I solve some of these problems with an index on shape and color? And yes, there are some benefits to doing that. You have to do some testing. But for right now, I'm just kind of bringing up the fact that the CE affects how they come up with their estimates. But remember, what goes into even these estimates are the statistics against the individual shapes and colors, for example. So if those are bad, then everything else is bad as well. So we kind of have a series of things we want to check on. Like, are our stats good? Do we have enough of them? Are they up to date? Are they accurate? And when we've checked all of those things, then we can go on and do something like, okay, maybe it's the CE. Maybe I should change the CE for this query and see if changing the CE to whichever one I'm not using by default, see if that impacts the query. And as we find that that may help, then we can use that, right? And if that doesn't help, maybe there's some further things we could do, like adding maybe more indexes, okay? So as far as cardinality estimation, I personally wouldn't recommend that you get wrapped up in every little individual calculation. I really want you to get wrapped up more in feeding information to the optimizer that is as optimal and as accurate as possible, especially when there are some specific limitations that we can work around, okay? And that there are options to basically give better numbers to the optimizer. So let's start with, and I've already mentioned multi-column indexes and statistics can definitely help. They're not always the solution to all of these things, but they can definitely help. So that's something else that you might want to try. But I really want to focus more on, okay, what if it's the stats that are bad and so forth? So let me just summarize a little bit more of this cardinality estimation stuff. There are different cardinality estimation models across the different versions of SQL Server. And like I said, the legacy CE refers to the model that was introduced in 7.0 and goes all the way up to 2012. But in 2014, they have a new CE. So this is how you can determine what your cardinality estimation model is up to 2014. But of course, in 2016, 2017, 2019, we also have the scoped configuration. So that's what I wanted to stress here, is that we can, and it's kind of in the middle of the slide, in 2016, you can set your database compatibility model to, 120, 130, 150, right? We can set it to the higher version, the version of SQL Server, but we can still set our legacy CE using the scoped configuration. Now, if you really want to get into some great information on the numbers and some of what went into the new CE, Joe's white paper is fantastic. But again, I want the information that goes into the calculations, not the calculations so much to drive how I optimize SQL Server. I want, it reminds me of Cuba Gooding Jr. and Jerry Maguire, help me help you. Well, actually, I guess that was Tom Cruise saying to Cuba Gooding Jr., help me help you. And this is kind of my thought on SQL Server. I want to help SQL Server come up with the best estimates possible. So I want to give it and make sure that the information that feeds into the process of optimization is as accurate as possible. So how am I going to do that? From a migration perspective, remember, I kind of recommend that a lot of you, especially if you have older databases, you leave the CE with the legacy CE, but you upgrade the compatibility mode to the current version so that you get all the optimizer hotfixes up to RTM, but you use the legacy CE because your database may be more balanced and optimized for that. Then, as you test, you can switch over to the new CE and kind of go from there. So those are kind of my recommendations for upgrading. But now, what about statistics, okay? Because that's really the main point of this session, right? We know we don't have a caching problem. We know that SQL Server is just not getting the right estimates. Now, it could be cardinality estimation, but again, that's something that we can try after we've made sure that the statistics are in good shape, good health. So what we're going to do is talk about some of the limitations of statistics, which happen if SQL has to do sampling. Some of the limitations also occur in the way that the histogram is built. And there are some scenarios that are just very hard for anyone to calculate in terms of an estimate, like when you have very weird distribution across your data. And I'm going to show you a scenario for that one. So let's start with sampling. SQL Server, when it updates stats, can't possibly look at, however many trillions of rows if you have that many rows. So after, and it's actually a much smaller number than this, but after about 80 meg, SQL Server starts to back off and kind of do sampling of your data. Instead of reading 100% of your data, it starts to read, 99, 98, 97. And again, the percentage that SQL Server samples isn't really the issue. It's whether or not sampling is good for your data set. Now, if your data is perfectly evenly distributed, sampling probably isn't going to cause you much grief. So here's my recommendation. If you are looking at a query plan and the estimate is off from actual, and you kind of go, okay, I wonder what the issue is. First thing I would do when you look at the statistics, in the statistics header using DBCC show statistics, and I will show you one in a moment, but in DBCC show statistics, you can see the amount of data in the table and the amount of data that was read to generate the statistic. And if they were sampled, right, then what I might first do is just do a regular update of stats, like especially if they're old, right? So if they're sampled and they're old, the first thing I'm going to do is just see if updating them fixes it. So I might just do a regular update stats, run my query again. If my estimate is still off from actual, then I might do an update stats with full scan and then see if my estimate is still off from actual. So what I'm trying to do is basically reconcile, are my stats up to date? And does that fix my problem? Because if that fixes my problem, maybe I just need to increase the frequency with which I update my stats. But if they're still off after updating and I find that they're sampled, right? Then I update stats with full scan and find that updating stats with full scan solves my problem. Then what I might want to do is either, and this is a little bit of a tough one, but you could disable auto updating for that statistic and then make sure that you have a job that updates the stats with full scan. The way that you can disable updating stats with sampling is to basically use the no recompute option at the statistics level or the statistics no recompute option at the index level. But then you better make sure that you're doing an update statistics very regularly to get around the fact that you've turned off auto updating for that statistic. But I don't turn off auto updating at the database level. Okay. And in fact, it's debatable as to whether or not you want to turn off auto updating, because if you increase the updating that you're going to do, then you probably wouldn't be auto updating either, because you'd be updating more frequently. So auto updating wouldn't kick in. But even how auto updating works has changed across the different releases. I'm not going to all that here. You can read about that in books online. But simply put, if you find that sampling causes you grief, then you may want to increase the frequency and do updates with full scan. But some of your tables are really large. Now that's where things like partitioning can help and incremental updates with statistics. I don't have an infinite amount of time here, so I'm not talking about partitioning and incremental stats here, but I do have some hidden slides that you can look at that will give you some insight. I'm just kind of talking about sampling in general at this point. Okay, so now a bigger problem that I think is incredibly frustrating, but I have a solution. I kind of wish SQL Server would do some of this for me, but the fact that I can do this, I'm fine with. So the histogram itself is limited to 200 steps. It's been this way for a while. It actually turns out that it's been this way since 2000. I think 7.0 was 300 steps, and then 2000 went to 200 steps, ironically. And it really hasn't increased from here unless we do something ourselves. Essentially, you can get more statistics by using filtered statistics. But let's talk about first what the problem is. A histogram stores actual values from the first column or the high order element of your index. So if your index is last name, first name, middle initial, then we will store up to 200 distinct last names in a histogram. Now, When your data is nice and evenly distributed, a histogram doesn't have to store every value to get good information about your data. But the more and more and more skewed that data set is, the harder and harder it is for SQL Server to store 200 values and know what the data looks like between every one of those values. Because if it's not consistent, if it's not evenly distributed, all we end up knowing between these step values are the averages between the ranges. And as your tables get larger and larger and larger, even the averages between the ranges don't end up telling us enough good information about that data. So here's where we start to come up with a really big issue, is around our data distribution. And the craziest thing here is, even though SQL Server has better ways of updating statistics without having to read the whole data set like incremental, even if it updates the statistics more efficiently, the actual statistic used by the optimizer is always a table level statistic, even when your table is partitioned. So unfortunately, even though they have made some changes to optimizing the process of updating statistics, the actual statistic itself that's used is sometimes not as optimal, even though they've optimized the process of getting the information. So what I mean by this is that histogram is sometimes less and less accurate the larger and larger your data sets become. And in fact, you can have skew at fairly even small data sets, but I promise you, as your data sets get into the tens of gigabytes and certainly terabytes, you are probably going to have trouble with those statistics giving you really accurate information about that data. So I tend to think of it like this. If you look on the middle of the slide, if you think of sales per product, and you think of like Microsoft products for a second, if we look across the entire spectrum of every Microsoft product, SQL Server has a lot of sales, Office has a lot of sales, Windows has a lot of sales. Microsoft Bob, not so many sales, right? So the point is, sales per product is all over the place and wildly varying. If you think of sales per customer, that is also wildly varying. I mean, there's customers that may have only bought one or two things. There's small businesses that have bought, a few dozen things. There's medium businesses. There's large businesses. There's government businesses. Again, how do we describe sales per customer when we only have 200 steps and then the averages between those steps? Eventually, those averages are going to be not very good, and we're going to have estimates that are just wrong and inaccurate. And so the long story short is, filtered stats can really help us. And I have a great demo and a great set of scripts that can really walk you through this. Again, to keep us on track and to show more stuff, I'm going to skip that, but I'm going to give you all the scripts to play around with this. And there is a recording of this demo that is a free recording that is associated with a past session that I did a few years ago. So I'll point you to all of that stuff so you can spend more time on this example. But I just want to explain what I do to make this much, much better. And I've got the blog post listed here as well on this slide. But filtered stats essentially allow you to create more steps across that large data set. And as SQL Server ends up using just one of those particular filtered stats, SQL's estimates will be more accurate. There's limitations to filtered stats. To be honest, you might be better off having smaller tables and maybe having more tables and then unioning those together in views. It's actually kind of an older way of partitioning your data called partitioned views. I'm a huge fan of partitioned views. It's something I do very often for VLTs, and it can actually get you better estimates, but you have to be careful that you don't have too many tables. So there's a lot to that strategy of dealing with these large data sets. My point is that filtered stats are an interim way of dealing with a large table, even a partitioned table, and at least getting better estimates. And what'll end up happening is SQL Server will use these smaller but more accurate statistics for your queries when that filtered statistic effectively covers that predicate. So there's a rule. SQL Server can use only one statistic per query. So if you've got two predicates or two conditions and one of those conditions is covered by a filtered stat and one of them isn't, they won't use the filtered stat. They'll use the big statistic, which is more lossy. But if you're looking for a specific value, instead of using the average, if there's a smaller stat, they can go to that. So you can sometimes really, really help your VLTs, especially in cases where the queries are narrow, but where the estimates aren't good. So like estimates off from actual. You've tried updating, didn't help. Estimates off from actual. You tried updating with full scan, doesn't help, right? And you look and you kind of go back to that table and you start to realize that the estimates and the averages are just not as accurate as you want. That's where filtered stats come in. For point queries or narrow queries where the estimates are relying on averages, but the averages are just covering essentially too much data and they cannot describe that average very well. So I've got a lot in the blog post and the session, and you can play around with this, but I've got another scenario that I think is really cool to demo. So I'm going to show you this one. Now, uneven distribution, or what SQL Server may think your data looks like, but what your data actually looks like. I remember the first time I ever saw this. But imagine you have, I did a simple example for the slide. So imagine you have 90 rows in a table. 10 rows are whatever it is that you're looking for, okay? They have a value of whatever for whatever column. Like, so 10 out of 90 is essentially what you're looking for. The question is, where in that table are those 10 rows? Like, they could be like 1 in every 9 is roughly the value that you're looking for. So like the idea is it's kind of evenly distributed, right? But what if all of the data is kind of in one place in your table, right? And I know you're probably looking at me like, well, what does she mean? I have different indexes and different orders, and I don't understand where the data lives within the index would affect the query. Okay, so let's explain what this means. So imagine this scenario, and I did this with AdventureWorks DW 2012, DW 2014, DW 2016. In fact, the one I'm going to demo on is 2016. It doesn't matter. I just started doing this demo after DW 2012, so you guys would have a nice, simple database that you could pull from and see. So Fact Internet Sales in DW 2012 has 60,000 rows. I write a little query that creates some nulls, and I end up making 2,500 rows have a null for ship date. And the question is, where are those null values? And if you think about it, if I just have an index on ship date key, right? Ship date, they could find those 2,100 nulls and then look up order date, put that into a work table, sort to find the min. That sounds a little expensive, although that's not that bad, to be honest. Or they could take an index on order date, right? And they could look into the table to see if it's null. Look into the table to see if it's null. Look into the table and see if it's null. And here's the problem. If you do that math, 60,000 divided by 2,500, essentially, you get 23. So SQL Server basically thinks that 1 in every 23 rows is going to be a null. And if it thinks those are evenly distributed, it thinks that within 23 rows, it would probably find a null. So instead of having to look up 2,500 rows, build a work table and sort, all we'd have to do is look up 23, and within 23, we may have found our null row. So SQL Server says, that sounds good. Now, realize these are narrow single column indexes. That's part of our problem. And this is one of the recurring themes that I have in a lot of my sessions, which is narrow non-clustered indexes don't have as many uses as wider, more thought out indexes. And I love this example for this point exactly. Okay, so let me show you this demo. Okay, so what I've got here, And let me switch over. Okay, so what I've got here, I've got two versions of this, and I've run it in a small database and in a big database so that you can see a few things. Okay, so in AdventureWorks DW 2016, and it doesn't matter which one you use, okay, I have basically created a copy of the Fact Internet Sales table, and I've called it Fact Internet Sales 2, and I will just quickly go and do this so that you can see the table. Well, and I'll do a quick SP help on it. So you can see that it doesn't have any indexes. It just has the same columns that we have over in Fact Internet Sales. And if I grab a few rows, you can see that they're actually using integer for a lot of these date keys. And there's pros and cons to doing that. But I'll just kind of move on and say, how do we make some of the values nullable? Well, the first thing we have to do is make the ship date key column nullable. So I'm going to do that here. Okay, and then I'm just going to simply, and I'm going to make it so that we're going to take a certain number of our sales, and starting kind of towards the end, I'm going to make every third row null. And that's kind of what would happen in the real world, right? You've got your sales from whatever the starting date is to the most recent sales, and it's probably not the really old sales that haven't been shipped. It's the new sales that haven't been shipped. So I want to make sure that we can see just some of those towards the end. So that's what I'm going to do. I'm going to say sales order number 7,200. I'm going to start at that value, and then number mod 3 equals 0. So I'm going to make 2,500 rows. Let's just run that so I can show you the 2,500 rows there. And then if I do that math, and I just have the select hidden there, but I get 23.769. Okay. Now, I do want to make sure that I have an index on order date and another index individually on ship date. Now, this is really not the best because SQL Server doesn't understand the correlation between these columns. So I create these two individual indexes. Again, very common that people have a whole bunch of narrow, non-clustered indexes. And if I quickly look at all of my indexes on Fact Internet Sales 2, I'm using my own version of SP Help Index because it has a few other things that I sometimes like to look at. This is all I've got right now on this Fact Internet Sales 2 table is just ship date and order date. Okay, nothing else. Now, if I go and I run my queries, statistics.io and statistics time on, and I basically say, do a table scan. I say, do whatever you want in this one. But in this one, I say, I want you to use the index ship date key. Okay, so I run these three. Okay, and I just want to look to see if there's anything else that I have in here. Yeah, okay. So I run these three, and I have show plan on. So I just turned that on right here. And I turn this on, I run it. Okay, it came back pretty quickly. So you might say, that didn't seem too bad. If I look at the execution plan, 21, 2, and 78. Now, from SQL Server's perspective, this middle one seems like that's the winner, right? It seems like that's only going to be 2%. Now, some of you that know a little bit more about show plan know there's already some things that look pretty dodgy in that second one, and that's that it says 52,000 of 24. So we know the estimate is way off there. So if I hover over that and I look, we can see the estimated number of rows is 23.769. That should sound familiar, right? But the actual number of rows is 52,773. So let's say you ran that query because the other ones were forced, right? So that's what SQL Server is going to choose to do. And it's slow. And you're like, what is going on here? The estimate's way off. So you update stats. Same estimate. Update stats full scan. Same estimate. SQL Server is not going to get a better estimate here because it doesn't understand the correlation between those two columns. So ultimately, we're kind of down to this. What do we do, right? And you can see, IO-wise as well, right? You can see 1,200 IOs in that first one, 52,000 in the second one, and 2,500 in this third one. So obviously that doesn't look good IO-wise either. And if you really want to play around with this, I've got cold cache, so you can clear cache and try things out. But ultimately it comes down to kind of how your table is indexed And we're going to do a lot better off, if you think about it, if we have some correlation between sales order date and whether or not it shipped. Okay. Now, I will have to tell you that SQL Server is kind of giving you some hints with the green hints. But here's an interesting case where the green hint is actually not perfect. It's actually not as optimal as we could do. And in fact, this is another really cool thing to kind of show you. Now, so far, my table is a heap, which is also not as optimal as I generally like. So my script does a whole bunch of stuff here. I kind of say, okay, first of all, well, what if the table is clustered and has a better clustered index? Sales order number and sales order line number would be the right clustered index in this case, and that would match or mirror your fact internet sales table as well. So I'm going to go ahead and create that. Okay, I'm going to do a recompilation so I don't get any textual matching or anything, but now that we've changed indexes, right? And I do my drop clean buffers with my table scan in the first one, my do whatever you want version in the second one, and then the third one I force ship date, which this is the one that grabs all 2,500 rows and then sorts to find the min, right? And again, I run these, and I'm doing this on a small table with only 60,000 rows, so it doesn't take too long. But check this out, 12, this is milliseconds, by the way, 270 milliseconds and 128 milliseconds. So this middle one is the slowest, although again, 270 milliseconds, who cares? But it still thinks that's the fastest. And let me tell you, the bigger and bigger the data set, the worse and worse and worse this becomes. In fact, over on this other window, I have a data set of 30 million rows. And check out these numbers for a second. Actually, go to the results window. So the table scan takes 2 seconds. Using the order date key, the one the optimizer thinks is best, takes 70 seconds. Whereas using the ship date and actually doing that sort, right, the third thing, and doing that sort to find the min, right? So they're using the index, doing the lookups for all, in this case, it's like 130,000 rows out of the 31 million. So it's actually even only 1 in 210 instead of 1 in 23. So it's a far smaller percentage, but because there's so much data here, it's absolutely abysmal, right? So again, looking at the plan and then back to the results here. So 70 seconds versus 225. So in fact, doing the work table and actually doing the lookups for all, in this case, 130,000 rows is faster than doing the table scan as your tables get larger and larger. So like looking at their plans, you know, what they thought, just looking at the first three, because the last two are definitely way, way better. But looking at these three, like they still think this is 0. They still think this is 53 and this one is 46. When if you actually look, it's the worst, what they thought was the best, and what they thought was the second worst was still better than what they're currently showing here. The table scan is kind of in the middle, right? Now, the other two are way better. So let me show you back to, it doesn't matter which one I show you, but I'll go back here. This recommendation is to have an index which includes both of those columns, or I should say, has both of those columns in it. They want you to put, and again, let me hover over this, they want you to put ship date in the key, and then they want you to include the order date. So what that means, okay, if we went with the green hint, is they'd have ship date in the key, but they'd have to look up the order date, which means for however many rows there are nulls. So in our original example, that's 2,500 rows. They'd still have to look up all the order dates and then find the min, because includes are not ordered. So this is good, don't get me wrong, right? This is a good index. But I would argue that if we had an index that was on ship date key and had order date key in it as well, we could actually find the min without having to do that sort at all. So I'm gonna create both of those indexes. And again, in my small database, all of this happens really, really quickly, okay? But what I'm gonna do at the very bottom here is I'm gonna show you the scan, the original use order date scenario, and then the ship date scenario goes to here. And then these last two, this one, ship date, order date index, is the one that the missing index DMVs recommended. And this very last one is the one I'm recommending, which is the one that's seekable. But notice I don't even have to force that one because SQL Server is going to choose that one. So I go ahead and I run these. Now here, I mean, it's almost a joke, right? 15 milliseconds, 274 milliseconds, 131 milliseconds. Okay, 2 and 1 millisecond. That's pretty cool, right? That will always be very, very fast. The thing that's really the clincher is looking in the big table, right? 2 seconds for the scan, 70 seconds for that terrible choice that SQL Server would have made on its own without having a better index. Now this, the ship date key index, would have been the best to force in the interim, but I'm much better off with an index that has ship date and order date in the key because the very first row in the nulls will be the min. So we just have one seek to basically do. So no matter how big our table, this number will always be incredibly low. Whereas including the order date, like the green hint said, helps, but we still have to do the sort. And the bigger and bigger and bigger your tables are, the more and more data we're going to have to sort. So the higher this becomes. Now, 30 milliseconds, 1 millisecond, 1 millisecond, your users aren't going to notice that. But as your tables get bigger, this is huge. This is definitely something that can become more and more of an issue. So I love this example because it does really a few things. I mean, it's showing us estimates that are off from actual, and it's showing a decision that SQL Server just can't seem to arrive at on its own. And that really is true. There are cases where SQL Server is not going to be able to arrive at that right index on its own. So the long story short is there are cases where sometimes it is really better to index, right? Where you really are going to want an index. So there's kind of a sequence of things that I would do to make sure that your environment is optimal. And I would always try to do the least expensive thing rather than the most expensive thing first. So statistics might help, but they might not, right? So first thing, can I update them and use sampling? But is sampling an issue? Can I update them with full scan? Is it maybe filtered stats that can help me? Or is it really I need a better index that's a wider index that can better help SQL Server with the correlation of those columns? And that's really ultimately going to be the only thing that works here. And this was the small scenario, so I don't know really how exciting that is. But go ahead and play around with this because I think it's amazing to kind of think through the process here and look at what your options are. So the long story short, as we get to the end of the session, I didn't know why that didn't click for me, but it is true that the right indexes are always going to work. I mean, to be honest, you can index the heck out of every single query if you had the disk space. And if you're read-only, yeah, you probably will go with more indexes rather than an environment that's got to be a hybrid of OLTP and decision support. But since so many of you are doing analysis, more real-time analysis in your OLTP environments, indexing is just absolutely critical. And we have to have the balance between too many and too few. So we really need to work on having the right indexes. So our combination really should always be, can I do better with my stats being updated? Do I need full scan? Do I need to maybe change my code? Do I need, because maybe sometimes a query rewrite can help. Can I get away with adding some filtered stats to help my problem queries, right? Or do I really need to look at and reevaluate indexes? So there's multiple levels here that you need to consider. You don't want to just index everything, and you don't always want to just trust the green hint. The green hint might get you closer to what a good index is, and I would always look at that, but you may want to think through like what maybe some other options would be as well, because you might find that there are cases where you can even do better than the green hint. So I love this session because it gets us to the next level after we know that it's not a caching problem, but there's still a lot of different things that might resolve our actual problem. So it is impossible to correctly estimate everything all the time. And a lot of the different assertions that SQL Server makes across the CEs work for some scenarios incredibly well, but they might be terrible for others. I don't get wrapped up. I mean, yeah, I do know some of the calculations and I do figure that out sometimes, but for me, it's more about giving the information to the optimizer that's as effective as possible. So these are the things that I've been talking about. Are they current? Are they with sampling? What CE am I using? Can I rewrite the query? Can I create an index, right? These are the things that I'm going to think about when it comes to trying to optimize my environment when I know it's not a caching problem. So that's it for this session. I will stick around for more questions. And I hope you guys enjoyed this. I hope you've had a great SQL Bits. I think we're just about at the end of the show here. So thank you very much and have a great night. There's a bunch of other resources here. And I'll just kind of cruise through these pretty quickly and fill out your evals, do all that good stuff. And I hope to see you next time. Thank you very much.